Okay, let's go. So welcome H3GT, my first digital lesson for you guys. I want to take a look at 5.2. I think I'm also going to record a video of 5.1, but for now let's go towards the week homework. I think it's very valuable to also do 5.1, but let's start at 5.2. So what you need to know is that we have something called energy, and energy you can transfer when it goes to one thing to the other. So in this example, you see this picture here, we have a cyclist. So when the cyclist is cycling over here, he has a certain speed. And when we're talking about energy, whenever you talk about motion and movement, we always talk about kinetic energy. So whenever someone is moving, he's cycling over here, he has a certain amount of kinetic energy. When we're doing physics in the bovenbouw, you will go do calculations with this. For now, we'll leave it as you need to know what it is. So kinetic energy is whenever you move, you have a certain amount of energy. I hope most of you can imagine that whenever you go up a hill, you lose speed. Huh? This is linked because you have to overcome something we call gravity. You go from a lower surface to a higher surface, so you conquer gravity. What happens when you're talking about energy is that kinetic energy is then transferred to potential energy. In Dutch you could say bewegingsenergie goes to hoogte-energie. Potentiële energie is always linked to hoogte-energie. So whenever you go up a hill, kinetic energy is transferred to potential energy. And as a result you also slow down a little bit. Or if you don't do extra movement, you actually slow down completely. When you're on top of the hill, you can also go down it. So you are very high up the mountain, so you have a lot of potential energy, veel hoogte-energie. When you then go down, you start accelerating again because you have the reverse effect than going up the mountain. So your potential energy is then transferred to kinetic energy, making you go faster again. So remember, when you go from kinetic energy to potential energy, you slow down because you are overcoming gravity. Whenever you go down a hill, you transfer your potential energy, your hoogte-energie, to your kinetic energy, movement energy. And to do all these things, we need to do something called work. So work is the amount of force you put into it over a certain distance. And it's always linked to energy. So whenever you calculate work, you get something in joule, the main unit for energy. So kinetic energy, like I said, is motion for energy. You can also lose this energy on a different way. Normally when you're cycling, you can also brake. So whenever you brake, remember your wheel is locked by these small brake pedals, and therefore you produce a lot of wrijving, friction, and therefore you produce a lot of heat. So you can also transfer kinetic energy to heat, and in this case, therefore you lose your velocity or you will slow down. Then we're talking about something about efficiency. So again, last paragraph 5.1 was about efficiency, and if you don't remember anymore, this formula was linked to it. So this N, eta, says about something about how much of the total energy goes towards something you needed. The E stands for energy, and useful is obviously what you want to use it for, and everything else is wasted. And if you look into two types of vehicles, we have vehicles that use fossil fuels. Fossil fuels, I mean petrol, diesel, but also something we call LPG, which is gas. You can drive on gas. And when you use these type of vehicles, often you have an efficiency of only 40 to 50%, meaning that for every liter you burn, only 40 or 50% of the energy that is released goes to something useful to drive your car. On the other hand, an electromotor, for instance, has a much higher efficiency. Whenever you use a battery, an electromotor, almost 90 to 97% of all the energy that is released goes towards moving your car. So you could say that the electromotor is way more efficient. We can use these numbers and these formula to calculate how much fuel is needed to drive 100 kilometers. We call this the consumption. You can ask your parents, so whenever they are driving, we're never talking about how much fuel we use, but we're always comparing it on a normalized scale. How much liter do you use every 100 kilometer? And if this number is lower, let's say it's below 5, you drive relatively cheaply. If this is a high number, let's say we have a Dodge Ram, this could go up to 30, so you use a lot of fuel to drive the same distance. And every liter of fuel costs a certain amount of euro, so that's important. You want this to be as low as possible. The required energy used depends on a lot of things. So it's not just the distance traveled. If you drive further, of course you use more fuel, but it also has to do with friction forces. So remember the things that implement friction. So it's the type of tire that you use, the type of road matters, but also whether or not there's a lot of wind, because when there's more drag, you also have to put in more force, so you have to put in more work. All these things are related. Linked to these are a couple of exercises. I put this in the PLT. So in Teams there's a PLT with exactly these exercises, so you know what to do. Then we also have the formula linked to it, because I'm talking about work, but work actually has a formula. The Dutch word for work, by the way, is arbeid. So whenever you go to the bovenbouw, we talk about arbeid, not work. But for now, the formula makes sense because, again, capital W stands for work. I told you already that whenever you have a certain amount of work, it's linked to a certain amount of joule. So it's linked to 10,000 joule or a million joule, depending on what happens. Abbreviations W and the J. So W for work, the J for joule. Makes sense. Most of these make sense. Again, we use force and distance again, just like last chapter. Capital F for force in Newton, and the distance from the S spatium is meter in meter. So sometimes you have to convert units. Remember, if the distance is given in kilometers, 1,000 meter is 1 kilometer, or when it's given in millimeters, it's 1,000th of a meter, etc., etc. Same goes for force. We'll look at a couple of numbers when we get there. And also something you need to remember from last chapter, a constant speed, the forward force is similar to the opposing force, and this can be very important. So let's say you only know the opposing force, you know the friction forces of the vehicle. You could then panic and think, oh, I don't have enough information to calculate the work. However, often in the examples, you can assume, or it's given, that the vehicle has a constant speed. And whenever something has a constant speed, remember, the net force is 0. And because the net force is 0, the forward force is equal to the opposing force. So because you know how much friction there is, you instantly also know how much the forward force is. And we can use that. Let's see in the next example. It's one of the questions in the book. So again, consumption is how many liters you use for this vehicle when you travel 100k. And we're going to look into a gas car. So the LPG stands for liquid petrol gas. And in this case, it has an efficiency of 30%. So of all the energy produced when burning the gas, only 30% can go towards moving the car. The rest is lost, probably to heat. We know that an opposing force of 630 Newton, and we need to calculate first the work needed to drive 100 kilometer, and then calculate the work how much we can drive on 1 liter, provided then 1 liter of LPG gives 24 megajoule. We'll look into C when we get there. So first A. Remember, when we know opposing force, we often know that we also all know the motor force. So in this case, the car is probably driving a constant speed. So therefore, the opposing force of 630 Newton is equal to our motor force. And remember, when something is constant, net force is 0. So we can just straight in fill the formula. Remember though, this is in kilometer, we need to convert this first to meters. 100 kilometer means it's 100,000 meter. And then I would like you to write down an answer such as this. First, the formula, W is capital F times capital S. So the force is equal to the opposing force, 630 Newton. And the distance we're driving is not 100 kilometer, but 100,000 meter. Please do that, otherwise you screw up this answer and you get up a couple of thousand short. So 630 times 100,000 is 663 million joule. You can leave it like this. You can also write it down as kilowatt hour. Remember, when you go from joule to kilowatt hours, divide by 3.6 million. For now, we'll just leave it like this. If I don't ask, you can just leave it like that. Now we need to look towards the how much work is provided by 1 liter. So we know that 1 liter gives you 24 mJ. So the capital M stands for mega, the small m for milli, so that's 1,000. But mega means a million. So 24 million joule, or 24 with 6 zeros. What we know is that you have, this is the amount of energy released when you burn 1 liter of gas. And we know that only 30% of whatever energy is released goes towards moving the car. So we need to use the efficiency. You could do it like this, because some calculators can actually implement this. You could do 30% of 24, you get 7.2 mJ, megajoule, or 7,200,000 joule. I personally prefer to write it out. So you can enter this in your calculator and you'll find this answer. If you do so, that's fine by me. I prefer to do it like this. 30 divided by 100, and you get a fraction of 0.3. You multiply that by 24 and you also get your answer. This also works if your calculator cannot handle calculating percentages. So now we know how much energy, how many joules is required to drive 100 kilometers, and we know how many energy goes towards our engine, towards moving our car, with 1 liter of gas. And now we can calculate how many liters we need to drive this 100 kilometers by just dividing them to each other. This is the amount of energy required to drive 100 kilometers. This is the amount of energy that is released, or at least that goes towards our engine when burning 1 liter of gas. So in total we require 8.75 liter to drive 100k. That's it for now. I might, like I said, post another video about 5.1 because I saw that a lot of people were struggling with that as well. But for now we'll leave it at this, and I'll see you later today. Good luck!